I had to choose to the cloud when I hit record, by the way.
Should we give people 1 or 2 minutes to join? Or
Yeah, I think so.
Yeah.
It's kind of like when you microwave popcorn, right? You wait until the kernel's hot, right? I think we're
yeah.
I think we're good now, Roberta.
Yeah,
Yeah.
I think so too.
All right. Let's start recording then.
I've already started.
Oh, okay. Okay. Good morning, and thank you for joining us on 21st of December as we are very close to Christmas. This has been an extraordinary year where we had an amazing opportunity to start the VAST software seminar series with my co-host Alice Allen, who is here, and Michael Zingale and Katie Slaughter, who is traveling at the moment. And this initiative has been successful because of all of your participation and for joining us throughout the year for talks and being extremely active participants for questions and discussion sessions. So as we are so close to Christmas, we bring you a kind of virtual gift basket of talks where we have some brilliant astronomers who would be doing lightning talks of the excellent packages that they're developing. And so we have with us today, if you guys can wave, we have with us today Neven Caplar, Sally Dodson-Robinson, Camilla Pacifici, Alexander Smith-Clark, and Anwar Shajib. The first of the talk would be by Neven Caplar. Neven is a researcher at UW and an associate director for LSST Interdisciplinary Network for Collaboration and Computing. Neven is very interested in analysis of large data sets and variable sky research and would be telling us a bit about the LSST time series data package today. So Neven, if you want to start, the stage is yours.
Wonderful, thank you so much. So I'll talk a little bit about the package that we are calling LSSTseries. Okay, so what is it about? So as you might know, the LSST is coming and the first light is now expected in July 2024. And as you can see on the picture to the right, basically, there's only one crane left. So you know that it's close. The data release 1 will be already huge, 18 million objects, 350 million sources or detections, almost 1 trillion for sources. So it's a huge data set. And we are basically starting to treat astronomy in this with this telescope kind of like particle physics, where you will have so many objects that it will be kind of hard to keep track of all of them. So I will shortly talk about Link Framework. So what is it? It's the initiative to basically develop software where the pipelines end. You know, pipelines will bring all of these detections, all of these sources, but we want to enable scientists to work on this scale of data. And there are 3 parts of this initiative: the focus on solar system science, extragalactic science, like static science, and time domain science. And I will talk a little bit about that. So we want to make codes which researchers can use for LSST science. And what we did so far, we started in September. We basically surveyed what exists already. all the time domain codes that exist in astronomy, around 60 of those, and popular packages. And we have identified two main goals of the project. One is to be able to access LSST data easily, and also to be able to efficiently and scalably evaluate the algorithm on this huge amount of data. Ease of access is motivated by packages such as LightCurve. So, these packages, which are, if you go to LightCurve tutorial page, you can find eclipse a planet in like 3 lines of code. So, and that's what really drives its usage. And then another thing is, so we want to be flexible, but of course we want to be also specific to LSST and LSST science, such as be able to support multiband, time domain analysis, and large amounts of data. So in that goal in mind, we have some provisional milestones which we put for this package, and I will not go through all of them, but we are somewhere in the middle of these milestones. But as you can see, they are basically focused on scalability. To be able to run, so stats1j is some sort of variability function, to be able to run that on a simulated data, on the real data, on the scales of LSST, so on millions or billions of objects. So I will just a little bit talk about where we are in 1 or 2 instances, what we are doing. So in order to run analysis of large amounts of data, we were looking how can we import such amount of data and what is the best package to share it. So we looked at things like X-array and VIX. On the end, we ended up with a good old Dask, basically, for multiple reasons, basically to be able to interoperate with other packages which exist at UW and LSST universe. And at the moment, there are some tests that we did. We are able to show that we can operate on a single laptop, basically on millions of objects in like an order of minutes. And we are basically expanding that effort as we speak. And then this is like just example of a workflow. So where you basically have an ensemble, some sort of collection of objects, time domain objects, and then you can spread this over many cores, many partitions, and you can do a function that you wish. There is a warning inside just to show you that I actually ran this code, and then on the output you get some summary statistic for object as a function of its object ID. Okay, and this is actually my last slide. I wanted to mention some of the challenges that we are having at the moment in general. So main point is that as a package and as a work, we want to contribute to time domain and to LSST time domain ecosystem without duplicating effort. So there are multiple avenues which we are exploring in order to make sure that that's happening. One is that we are having monthly meeting and engineer exchange. So we have software engineers and they have software engineers with, for instance, alerts broker, one of these brokers, which takes alerts that LSST will produce and distributes to the broader community. Then we have monthly tech talks, which are link-wide, so LSST-wide thing. It's very similar to these talks that are happening once a month, and they showcase just the software work that's done by LSST community. And I do invite you to join if you're interested in this kind of work. It's every Thursday at 10 a.m. Pacific, and I think I left the link, but if you Google link or LSST and Tech Talks, I'm sure you will be able to find that. And then we are also trying to interact and collaborating with the science collaboration groups to make sure that there is no overlap. So for future, we have some things. How do we want to, if you have a package and we want to make sure and we want to help you to operate on LSST scale, how will we actually do that? Are we going to re-implement packages? Are we giving to our engineers just to wrap it smartly, etc.? The other problem is that LSST is much more complicated and there is more science than Caplar and tests. So how can we be most useful for community? What are these functions that we actually want to do? One of the initiatives that Link will have is these incubator projects where there will be money and software resources where scientists can apply to work with the team and implement their packages, and this is going to be, the call will be out in January, and we should start in the spring. Okay, so this is all I had in this small lightning talk. Thank you.
Thank you, Neven. That was perfectly on time. So for each talk, we're going to have a 5-minute talk and 1 minute for some quick questions. And then we would reserve longer questions for a discussion session that follows the talks. So if we have any quick questions, can you please raise your hand, or from Kelly? Kelly, do you want to open up your mic and ask the question, please? Oh, no. Okay. So Kelly asks if there is discussion board or Slack that you have currently.
Yes, so discussion board will be within LSST Slack. If you're on LSST Stack, and if you look for link, there will be many channels that you can find.
Okay, correct. And then I think there's another quick question, which is from Paul Barrett. Will I be able to use my own time series algorithms? And Paul uses Julia.
Okay, so those are questions which are very good questions, and I think we are a little bit still thinking about that. In general, yes, we are trying to make it that you can use it on any multi-band time series, like ZTF is our goal, our Pan-stars, but it is, so in general, yes, with some more applicability for LSST. Julia, at the moment, Python, of course, because scalability, be just as we are building up. Julia is something that I'm very interested in, and perhaps in the future.
Okay. All right. So with that, let's move on to our next speaker. Thank you, Neven. The next speaker is Sally Dodson-Robinson. Sally is an assistant professor at University of Texas, and Sally's research interests span planet formation, protoplanetary disk evolution, disk interaction, and debris disks. Sally would be talking about NWelch, a Python implementation of Welch's method for power spectra and Bohr.
Thank you so much. And I just want to make a quick correction, which is that actually I'm an associate professor at University of Delaware.
Sorry. Yeah.
No worries.
Yeah.
But I don't want my colleagues to get really irritated at me for not giving the correct affiliation. So my software package is called NWelch, and it is an implementation of Welch's method, and it detects oscillations in common to 2 time series, and it also produces power spectrum estimates with less variance than the Lomas-Gargle periodogram. So another time series another time series tool potentially relevant to LSST. So what was my motivation for developing this package? My motivation was actually radial velocity planet searches. So if you want to make sure that you have a true planet and not just a stellar activity signal like rotation.
Sally, I'm sorry, but I just see something saying loading. So maybe you're not sharing slides? Am I the only one?
I
also have a similar issue. It still says loading slides for me as well.
Okay.
Maybe just stop share and reshare.
Okay. Yeah. Let me try that.
Yeah, I think maybe getting out of the full screen mode might help in this case.
Yeah. Okay.
Yeah.
So we will go ahead and just leave it in this mode then. Sorry about that.
It's all good.
All right. So with planet searches, you want to make sure you have an actual planet, not just a signal from the star. And one way that you can do that is to analyze stellar activity indicators. And so if you have a signal in your activity indicator at the same frequency as your planet candidate, that is a clue that your planet is not an actual planet. One of the problems is that if you look at the middle plot here on the side, I have a simulated activity indicator, which is on the x-axis, and a simulated radial velocity signal on the y-axis. And if those two are out of phase, even if they share an oscillation, you make a plot of RV versus activity indicator, and it looks like a mess. So you mistakenly conclude that the two do not share an oscillation when in fact they actually do. And so the two signals that underlie this middle plot here are on top. X of t is an activity indicator that has a rotation signal. Y of t in red has the same rotation signal plus a planet signal with frequency f sub p. So it has both of those things. So the way that you can tell that these two actually do share an oscillation, even in the presence of noise, phase shift, a second oscillation, is you can take a cross correlation between the two of them, which we see on the bottom here, and then the oscillation that's shared is very obvious. So the problem is we have unevenly spaced data. So these are just some RV data sets from GJ 581 on the left and GJ 3998 on the right. So if your time intervals between observations aren't constant, then you can't actually calculate a cross correlation in the time domain. But what you can do is you can take a frequency domain view of the cross correlation. So what we actually do is we compute what the Fourier transform of the cross correlation would be. And the way we do that is simply by multiplying the Fourier transforms of our two time series, our radial velocity and activity indicator. Now, in order to do that, one really important thing is that you have to actually obtain multiple independent estimates of your Fourier transform of each time series. And that's where Welch's algorithm comes in order to do this. If you don't average together multiple independent estimates, you'll just get a nonsense answer in which the two time series are perfectly coherent at all frequencies. So we don't want that. So one nice artifact that you get from averaging together multiple estimates of your Fourier coefficients is that your power spectrum estimates can come out very clean. So here we have the GJ 581 time series. The radial velocities, the activity indicators H alpha are on top, the radial velocities are on the bottom. And in the light blue, you can see the Lohm-Scargill periodogram. And then in the dark blue, you can see the Welch's power spectrum estimates. And you can see that you have a much cleaner estimate due in part to your cleaner spectral window and partly due to just reducing the variance by averaging together your Fourier coefficients. And then in the dark blue with Welch's, you can immediately see the rotation, which is this leftmost vertical line. And then you can see the two harmonics of the rotation, which are the two further to the right vertical lines on this plot. And so the oscillations and the fact that they are rotation and harmonics are very obvious in the Welch's power spectrum estimate. And then here, we take the magnitude
1 minute
squared.
left.
Okay, so we take our magnitude squared coherence, which is simply just the cross correlation frequency domain view normalized by our two periodograms. And sure enough, what we can see is that so-called planets D and G are actually statistically significant signals in our magnitude squared coherence. And those are shown here in the yellow vertical highlighted regions. And then the dotted lines show harmonics at which there is a statistically significant coherence. So what we can see is that both the RV and the H alpha pick up your harmonics of the rotation very, very well. So this is a powerful planet validation tool. It's also great for just making nice power spectrum estimates. And here's the GitHub repository here. There is a nice demo notebook on how to use it, and I will go ahead and stop there.
Thank you. Do we have questions for Sally? Okay. Sally, I have one quick question. So compared to Lohm-Scargill, how does it compare when it comes to picking up different periods?
Yeah, so the advantage with Welch's algorithm is that your false alarm thresholds tend to be a lot more realistic. So you don't get as many false positives with Welch's as you do with Lohm-Scargill.
Yeah.
And then that's also due to the fact that you're suppressing your variance. So the disadvantage with Welch's algorithm is because you have to get multiple estimates of your Fourier coefficients. You do that by splitting your time series into different chunks. And so that decreases the time baseline that you get in any chunk, which means you don't have as good of a resolution in the frequency domain.
Yeah.
So if you want very long period signals, you might actually be better off with Lomscargel, but I've found I always use Welch's method now. I don't even compute Lomscargel periodograms anymore, just because I really appreciate the fact that you get much more consistent results.
Yeah. Thank you. I think we can, thank you, Sally, and we can now move on to our next speaker of the day, who is Camilla Pacifici. Camilla is a senior astronomical data scientist for JWST and has a lot of experience in developing JWST data analysis tools as the former project scientist for it. And also, Camilla was an instrument scientist for JWST NIRIS at the Canadian Space, for the CSA. So Camilla will be talking to us about Jdavis, and I would like to open up the floor for Camilla.
Thank you very much. Thank you for catching my recent change in job from project scientist, from instrument scientist to data scientist, still at the Space Telescope Science Institute, still for JWST. I would like to introduce you to Jdavis today, but first of all, give credit to the developers that worked on it. I'm just a manager here. I communicate with the scientists, I talk to the community, I figure out the needs of the community, then I work on prioritizing them, and I work with the developers to make it happen, but they are the ones who are actually making it happen. So we have an awesome team here. Okay, wait a second. Okay, so when JWST was still in preparation, we were tasked to create these data analysis tools. These are post-pipeline tools. There is the JWST calibration pipeline, and whatever gets out of it is ready for science, can be used in Jdavis or for data analysis in general. So JWST ZL2 is doing great, collecting photons, and is ready for science. I'm sure you have seen the beautiful images that came out. So the data analysis tools is not just Jdavis. So I want to give you the framework first. We're talking about libraries, we're talking about notebooks, and we're talking about the visualization tools. In terms of libraries, here at STSCI, we mainly focus on PhotoUtils, the AstroPy affiliated package for photometry, SpecUtils, which is the AstroPy affiliated package for spectroscopy, and SpecReduce, which is another AstroPy affiliated package, is fairly new. It's growing exponentially now, and it is to reduce spectra. So it would improve on what the JWST pipeline does already, but it's generic enough that it can be used with any data set. So this is not JWST specific. And there are a bunch of others, ASDEF, GWCS. I'm not going into those details, but just to give you the idea that everything I'm showing you today behind the scene is using those packages. The notebooks, we have collected a good number, like 20, 30 notebooks, where we explain the community how some tools work, and also we ask the community to tell us what they need, what is left that they would have to still implement themselves because it's not included in these libraries. And these are the JWST data analysis notebooks, and also we had some of these through the JWebinars, although that was more of an explanation of how the tools work, the pipeline, Jdavis, and other tools developed here. And so the focus of this talk is actually Jdavis, which is an interactive tool embedded in the Jupyter framework. The beauty of Jdavis is that it can work in a notebook, so you can do your analysis, then you open Jdavis, you do some of it, or a quick look in a GUI, and then you get out of it, you can export things from Jdavis and keep your workflow in the notebook. It can be embedded in a web page. MAST, the Mikulski Archive for Space Telescope, uses Jdavis. So you can quick look your data through Jdavis before downloading a massive amount of data set. And it works also as a standalone application if you prefer the way of 100 clicks to get things done. So for you, I have a few screenshots today, and hopefully they will spark your attention for Jdavis. This is the configuration spec viz. And I loaded a MIRI spectrum, JWST MIRI spectrum. There was an emission line in this spectrum, so I just selected a subset, opened the plugin for line analysis, and it gave me in a click all the properties of this emission line. Next configuration is MOSFES. This is specifically for multi-object spectroscopy. So if you have a large data set with a lot of spectra, you can load them into MOSFES and inspect them one by one. So MOSFES will show you the postage stamp of the image if you have to provide either the postage stamps or a filled image, and it will zoom based on array index, the 2D spectrum and the 1D spectrum for your data set. And this is the glass data set, is a nearest observation. And you can change the plot options, for example. In this one, I'm showing that. All the plugins that I'm showing are available in all configurations, most of them, depending on like spectroscopy, they have their own plugin, and imaging has different plugins, but they're all available. So line analysis would be available here as well.
Camilla, 1 minute left.
Yes, perfect. Third configuration is CubeVis. So this is for integral field unit observations. And I'm showing a cube. So that's on the left is the flux, on the right is the uncertainty cube. You can slice through the cube and you can see the collapse cube. That's a 1D spectrum for the collapse of the cube. I selected to emission line and I fitted a model to the continuum and to the lines. The model uses AstroPy modeling under the hood. This is an IMVIS, image viewer, simple, but gives also some photometry. We have a photometry plugin, so we can select regions in the image and get photometric observations. Quick look. And the last one is SpecVis 2D, where you can use SpecReduce under the hood to do extraction from 2D spectrum, from a 2D spectrum to a 1D spectrum. And there are multiple extraction options, background options, and so on. If you want to give it a try, it's a simple pip install. We release every couple of weeks because it's in heavy development. And there are a bunch of links that I have here, but you can also just reach us through the GitHub page if you want to submit an issue, if you want to contribute. Or I'll add my name to the my email address to the chat here if you want to contact me directly. Thank you.
Thank you, Camilla, for an excellent talk. We have one question in the chat, which is from Mark Pound, and Mark asks, while Jdavis is principally designed for JWST and IR optical data, could it be used for radio astronomical spectra, maps, or cubes?
Yes. We might not have a parser for your specific data set, but there are ways to just load the data set as a Spectrum 1D object. This is a bit misleading. It's called Spectrum 1D, but it loads cubes as well. It's a SpecUtils object. So you can load it as a SpecUtils object and load it into CubeVis and work with it.
Okay. Okay, great. Thank you for the answer. And let's welcome our next speaker, who is Alexander Smith Clark. Alexander is a computational astrophysics grad student at Stony Brook and was a Fulbright scholar, or has been a Fulbright scholar since 2016. Previously, Alexander was a professor at Universidad Católica de la Santísima Concepción in Chile. And so Alex would be talking to us about pynucastro. Take it away, Alex.
All right, thanks so much for the presentation. So, well, as you pointed out, okay, my name is Alexander Smith from the Stony Brook University, and I'm going to present pynucastro, visualizing and interfacing nuclear reaction networks. So now let me stop the full presentation mode. Here's much better. So, okay, so now let's begin my presentation formulating the problem. So in this case, okay, we may notice, okay, that in many astrophysical processes like nova explosions or nucleosynthesis calculations, we may have found the system of differential equations number 1, okay, which where the right-hand side of this system of equations represents a rate. each term that we have here, okay, for example, the red, the blue, and the brown one represents a rate that we can describe it in the following way, okay? For example, the red one represents a collision of two different nuclei. The blue one represents a collision of three different nuclei, and the third one represents annihilation of two equal I nuclei. So now we ask ourselves how we can accurately describe and facilitate the integration of the reaction network number one. And this is exactly how pynucastro enters into the scheme. So pynucastro is an open source code package, okay, that provides an interface to reactive database rates and tabular rates in order to accomplish two important goals. The first one is to evaluate the right-hand side of the system of equation number one, which is very nasty, okay, and facilitate the integration in Python and C++, and also supports GPU offloading. The next goal is to provide visualization tools in order to accurately depict the integration, the reaction network on consideration. So now, as an example, okay, we are going to describe succinctly how we can write a network to the 56 iron group. So pynucastro encompasses four important classes: the nuclei class, which contains all the information of the nuclei; the rate class, which encompasses all the required information to evaluate the rate and the captured energy; we have the rate class, the rate collection class, which encompasses all the tools that we described before; and finally the library class, which contains all the rates. So now in this slide we can see succinctly, okay, three important stages. We import, of course, all the required packages to perform the writing of the network. In the first three statements, we have very simple functions to create the reaction network, okay, excluding all the weak rates in this case. Then we compute the reverse rates using the tail balance and the use of partition function. And finally, we perform the writing, in this case in Python. So now, using these simple techniques, we can actually provide, okay, first, the evaluation of the right-hand side in the iron 56 script that we see before. We can provide the visualization of the network in this case, where each blue sphere corresponds to a nuclei and each link corresponds to a rate. And we can also perform the integration using the script that we wrote, okay? And we can, for example, in this case, we have the transient state and we have the NSE state. And pynucastro is also able to perform the calculation of the NSE state, okay? So in this slide, we can see that pynucastro has the ability to process the composition of the nuclear statistical equilibrium state, and we can compute the difference between both. And we can see that the difference, okay, in this case is around 0.1, where the absolute difference oscillates. And the reason for this is because we haven't incorporated the screening in this case. And also pynucastro possesses or has the ability to incorporate screening calculations, which is the last feature that we introduced in pynucastro. So as a summary, okay, pynucastro can perform two important goals: to evaluate the right-hand side of the system of the differential equations, number one, which is a stiff, okay, and provide visualization tools to accurately describe the reaction network on consideration. The second thing that pynucastro tackles is that we can export the code to C++ and perform GPU offloading in order to accelerate the reaction network calculations. And finally, pynucastro can incorporate screening routines and perform detailed balance inverse rate calculations with nuclear partition functions. So this point is very interesting because this is not done we are one of the first groups to implement this feature. And also we have a paper, okay, submitted now for approval, for reviewing. Sorry. So this is essentially why pynucastro can be very helpful in order to accomplish nuclear reaction calculations. Thanks so much.
Thank you, Alexander. Yeah. Do we have any questions for Alexander? Or if not, we can also reserve them for the discussion part later on. Let's thank Alexander again and move on to our final speaker of today, Anwar. So Anwar Shajib is a KICP and Einstein Fellow at the Kavli Institute, and Anwar got his PhD from UCLA. Anwar's research interests are gravitational lensing and observational cosmology, and he's also the co-PI for STRIDES collaboration that aims to discover strongly lensed quasars from DES. So Anwar, do you want to tell us about lens astronomy?
Yes, thanks a lot for the introduction, Amrita. So I'm going to give you a brief overview of this software, lenstronomy, which is a multi-purpose lens modeling software for strong lensing systems. As you can see on the slide, this is an AstroPy affiliated software. And the current core maintainers and developers are Simon Beer, Daniel Gilman, and myself. But there is a lot of contributors from the community. So I have a screenshot from the GitHub page of the software for the current contributors. You can see it's about 27 right now. There are about 90 to 100 active users of this software, and this software has already been used for 90 or so publications, and it's growing. So this one of the primary purposes of this software is forward lens modeling of strong lensing systems. So I will just give you a brief overview of what is done in the modeling process. So if we have an imaging data of a strong lensing system, as you can see here on the left, we want to reproduce this image from our model so that we can compute a likelihood function that we can optimize to get the best fit or the posterior of the model parameters. So in our model, we need to specify a few different components. So one is the mass distribution in the lensing galaxy in the center and also its light distribution. We also want to describe the flux distribution in the host galaxy of the quasar at the background. And we also need to know the point spread function. So when all of these different model components are specified, then lenstronomy, given the set of parameter values in these components, it'll predict or reconstruct the observed image, which you can see at the bottom of the slide. And then we compute a likelihood function that we can use for many different MC sampling algorithms. One strong feature of lenstronomy is that it's very modular. It can use many different choices for these components. So for example, for the deflector mass, you can either use a simple singular isothermal mass profile or a power law mass profile. You can also choose an NW mass profile. Or you can have cores in these mass profiles. For the light profiles, you can use elliptical Cersei, Harniquist, or Jaffe profiles, and there are many other different options as well. For PSF, you can either provide a pixelated description of the PSF, or you can use a parametric function like a Gaussian or Morphoid. So I will give you a few different applications of this software in different types of astrophysical and cosmological application. So one is to do a highly detailed lens modeling of a strong lensing system that is required for doing precision cosmology, for example, measuring the Hubble constant from time delays. So you can see here the system here is fairly complex. It has multiple different source components and also multiple different lens components. So and these different components are at different redshifts. So there are multiple different source planes and image planes. So the lenstronomy software does ray tracing through all of these different planes, and then it recreates the observed image. So basically in this illustration, from right to left, at the very back, there is the quasar host galaxy. There is a reconstruction of the flux distribution of the quasar host galaxy at redshift 2.3. And then in front of it, there is another source galaxy, which we call S2. And in front of that, there is another perturber along the line of sight, which is a galaxy at redshift 0.76. And finally, there is the final central lensing galaxy at redshift 0.6. So, so all of these different components, their light and mass, contributes to the overall lensing effect. And you can see lenstronomy recreates these very complicated lensing system very accurately. So another
Anwar, you have 1 minute left.
Okay, yeah. Another big application is dark matter physics, where we want to test different models of dark matter, and different models of dark matter has different prediction for how many dark substructures there will be in what mass function. So you can see like lenstronomy can simulate thousands of substructures and produces the lensing effect based on these different models. So on the right side, these are two representation of the projected surface density given two different dark matter models. It's also used for simulating training data set for machine learning, which is used to discover lensing systems. So on the left side, these are simulated training data sets, and on the right side, this training data set has been used to discover new systems from the DELV data. Given the modular features, like it's also possible to extend the use cases of lenstronomy to non-lensing applications too. So for example, here, lenstronomy has been used to do quasar host galaxy decomposition, which is basically applying lenstronomy by taking the quasar as a point source and the host galaxy just describing it with statistic profile without having any lensing element. And after that, the lenstronomy can just give you the associated light profiles or the flux distribution in the quasar and the host galaxy of the quasar. So you can see this is a snapshot of many different softwares that uses lenstronomy as the core engine. So and these different softwares are giving higher level APIs for users that make using some of the applications that I've showed you so far easier for people to use. So so it's a
We're at the end of the time. So if you want to go to the summary, that would be great. Thank you.
Yeah, so this is the last slide. So yeah, so this lenstronomy is a full ecosystem of many different softwares. Yeah, that's all from me. Thank you.
Okay, thank you, Anwar, and thanks to all of our speakers so far. Do we have any questions specifically for Anwar's talk before we move on to a community discussion? If not, we can also then move towards the general questions. Before we do that, I just want to mention that we do have a poster presentation for VAST at the AS 241 meeting on Monday, starting at 5:30 p.m., which is 9th of January, Monday. So if any one of you are there, come and find us and speak to us, and it would be great to meet you.
Rita, could I also make one comment?
Yeah.
We're also looking for a future presentation for people who are interested in demonstrating their workflow. If there's a set of tools, hopefully up-to-date tools that you use to get your day in and day out job done, we'd like for people to share that sort of as a demonstration mode in an upcoming seminar, just to help other people learn how people work, how people do their jobs. So if you're interested in that, if that person might be you, raise an issue on our GitHub page.
Yeah. Thank you, Michael, for bringing that up. And so the Q&A session would be chaired by Alice, and I would like Alice to take over the session now. Thank
Yes,
you.
but I'm happy to have people chime in with their questions or post them to the chat so we know that you have a question. So I do have a question for Neven. What language is LSSTseries written in?
So, it's basically all Python at the moment. And this
Python.
again is, general that astronomy uses Python, and LSST is Python with some C background, and that's driving. But exactly, when you're talking about scalability, yeah, you probably want to use different things. LSST solves that Python has a lot of C in the background.
Okay.
So that seems like a default option.
Okay, thank you. And Sally, I'm wondering if you're welcoming, are you looking for contributors to your code base?
Well, that's an interesting question. I can think of lots of ways to expand what I've done, and some of my students are working on them. But if anyone else has a good idea, if they want to submit a pull request or talk to me about it, I'm definitely open to ideas. One thing that I'm pursuing is possibly making a Julia version. I'm also expanding into other frequency domain methods. So there's definitely a lot more to do.
Okay. So did you hear that, Paul Barrett? Amrita, do you have a question? You have your hand raised.
Yeah, I have a question about Dusk. I think Neven mentioned that you're using Dusk. So I've been trying to use Dusk for some of the CDF data, and I keep running into some issues, which is parallelization in individual tasks, and it's just not a capability that Dusk has. And the other issue that I keep running into sometimes is the memory. My tasks finish up early, and there is a lot of data pileup that happens before you can go towards the final steps. So do you have any pointers about how you've been using Dusk or optimizing it?
Okay, I know that my collaborator Doug is here, so maybe he can comment a bit more. What I do know is that Dusk can be very finicky. Having said that, of course, exactly I wouldn't know. I don't know, Doug, are you here? Or he was here?
Yeah, I'm here. I'm Doug Branton. I'm a software engineer with Link Frameworks. Definitely feel your pain with Dask, because I've been learning a lot of the ropes over the last couple of weeks. Kind of the main point that I've been finding regarding the memory management is the more that you can do while you're operating on single partitions with single workers, just the better things are going to go, because Dask doesn't have intelligent ways of, when memory is dispersed across many partitions, of only accessing the minimum number of partition it needs to get the given subset of data out. So that's been one of the learning points for us. As far as the single processes point, I don't have like a clear answer to that. I think part of it is you have to provide Dask problems that are solvable with parallel workflows, and that requires some front on the problem side itself.
Thank you.
Yeah, was that helpful, Amrita?
Yeah.
One of the things I want to do is encourage all of the all software authors everywhere is to add citation information, how you want your code cited, to your GitHub repo and or code download site, because if other people are using your code, it should be cited. So if you can help people out by putting your preferred citation information on your GitHub repo, that would be fabulous. So please do that. Does anybody have other questions?
Alice, maybe we can ask people if they can share what their plans are or have been for publishing their codes. So we've heard about people using the software in published papers, but in order for especially the junior people to get recognition for the work they've done, publishing the code itself as a citable source is important. And so have people done that? I mean, we could just go through the packages. Lenstronomy. I know you're the ones who said you had 90 people using it. Have you
So lenstronomy already has published paper on the software on MinRes and also as JWST articles.
Oh, great.
So people can cite those papers. Yeah.
Awesome.
Yeah, and lenstronomy. I'm
We had
looking-
a JWST editor here for a moment, but I think he's departed. But indeed, if you haven't asked that question of your package, you should, because again, the people, especially junior people who are contributing, should get credit for the work they've done in the software. And JWST has been a fantastic avenue for that.
Yeah. JWST is really good if you've got a really complete package with documentation, because they do look to see whether you've got test suites and all of that. But not having that, and I do encourage people to use JWST, the Journal of Open. Do you want to provide a
Open
link?
source software.
Yeah, I'm just wondering if you want to provide a link to it. But if you don't have all of that, you can still have the software cited in numerous ways. And of course, I would encourage you to add it to the astrophysics source code library, which is at ascl.net, because that's also citable. And getting a DOI for it through Zenodo or another service is also a way that you can get citations that ADS can track. So whatever citation method you choose, you want to make sure that it's one that ADS can track.
So I have another question.
Sure.
Support for the software development. I heard at least one of the packages was AstroPi affiliated. I think that was lenstronomy again, although
There were a
Yeah.
couple of them
Yeah.
are. Yeah.
have others explored trying to get funding? We've heard in the past about people having success with Google Summer of Code. Some packages being directly NumFocus sponsored instead of through AstroPi's NumFocus sponsorship and so forth. Have people thought about this? If any of the different packages want to chime in.
I haven't tried NumFocus. I have tried to get funding for my software work just from standard NASA grants. In addition to developing more the mathematical methods side, I haven't been successful so far, but I have another proposal in, so we'll see how it goes.
Great.
On the topic of funding, I think it's worth mentioning, I don't have the call on the top of my head, but NASA TOPS, so we're entering the year of open science at NASA, and there's a whole initiative called TOPS, the transformation to open. I don't know what the P stands for. It might be open science. And so I can definitely send a mic to circulate out, or if Steve Crawford is here, I'm not sure if he is, to circulate some of the NASA opportunities for funding specifically for software development.
Thank you, Kelly.
Yeah, I found that link, Kelly. Thank you.
I found it seconds after you did, so. So, okay. Are there I'm wondering if there are projects that people here would like to see presented that we can ask for presentations. So, and what would you like to see VAST do in 2023? So
we've thought about workflows, as I mentioned. We also are starting to think about trying to get maybe people talking about funding and publication, things like that. So not software itself, but the support around software. But we're also interested in themes.
so
And I know you had something you wanted to share as well, Amrita, I think.
Oh, my idea was that we have been going through these talks with a lot of different people introducing their software packages and their communities. And we have about 270 or so people in this group, on the Google group. So I was wondering if it might be helpful to have kind of, we are looking to recruit people with specific expertise in to support our code. sort of a page, or like a help wanted page. I don't know what everyone thinks, but that could be something interesting.
I think one way to do that is if you want help and or are welcoming new contributors, please add that information to your GitHub repo.
Yeah.
So that's a good way to be welcoming, is to say, yes, we want your help, and here are some issues that people can work on, and there are tags in GitHub to say, you know, good for a first timer, kind of thing. So
yeah,
I think that would be really helpful.
Yeah, or posting in the Google group as well, for the community. If you want to post in the group, saying this is where we would appreciate your help, maybe.
So yeah, and if you have ideas for presentations that you'd like to see, you can file a GitHub issue with JWST to suggest one.
Okay.
So I'd like to thank all of our speakers. Thank you all for speaking. Yay! And if I don't have, I think that's it. I think we can wrap up. Yeah.
So Alice, I just posted in the chat. This is Kelly Cruz again from Flatiron Institute, and based in New York City, also Hunter College. And so Dan Foreman-Mackey, myself, and Adrian Price-Whelan hosted a software development workshop at the Flatiron Institute past spring. And we started a pretty nice Slack workspace dedicated to astronomically focused software development. And it was called Orca. And the two communities, this community and that community, are extremely complementary and overlap. And so one of the things, maybe we can chat at AAS about how to kind of combine these efforts to provide a Slack workspace. Because like what the previous person just spoke about was like, how do we recruit people to our projects and like advertise help wanted and things like that. I could see a Slack workspace being ideal for that type of community enhancement.
Okay. Yeah.
And I will say that one of the things we're looking at for the future is to have a roundtable discussion with VAST and PsyCodes. So expanding a little bit because there are some issues that are common to software development in all sciences. So we're thinking of doing a joint meeting with PsyCodes where we would have a roundtable discussion. So that's something that we may do in 2023 as well.
Can't believe it's going to be 2023.
I know. How is that possible? So okay, so I'm going to stop and turn it back over to Amrutha for.
Yeah, thank you again for all of you for making this community successful this year, and stay with us. We have interesting programs coming up through 2023, and if you are at AS, come say hello at our poster session on Monday, 9th of January at 5:30 p.m. And enjoy your holidays. Merry Christmas and Happy New Year to those who celebrate, and a Happy Hanukkah as well for people who are already celebrating. So, yeah. See you next year.
Thanks so much, Amrutha.
Thank you very much.
Thank you. We'll see you.
Happy holidays.
Alex, what's your weather like down there?
It's cold here, but it's not as cold as it is in
No, I was asking Alex.